In this video, we solve problem 13.9.012 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. The problem statement says the material for constructing the base of an open box costs 1.5 times as much per unit area as the material for constructing the sides. For a fixed amount of money C, find the dimensions of the box of largest volume that can be made. Let X, Y, and Z be the length, width, and height, respectively. To solve this problem, I would start by writing down everything that's given. It's always a good way to start an application problem. And then we probably also want to draw a picture. So we're going to draw an open box just to help us visualize what it is we're doing. Let's say my open box looks like this. Trying to draw it with some perspective. So that's my box. And maybe it looks like that because it's open. Now we were told to let X, Y, and Z represent the length, width, and height of this box respectively. So I will call that Z, and I will call this dimension X, and I'll call this dimension Y. Okay, let's see, what else is given? We're told that the material for constructing the base costs 1.5 times as much per unit area as the material for constructing the sides. Okay, what else? We're told that we have a fixed amount of money C. So this is the total cost, and it's fixed. Maybe you have $100, and that's exactly how much you're going to spend. But we don't actually know how much it is. We just know that it's fixed, and it's a constant amount. We're asked to find the dimensions of the box of largest volume that can be made. So we want to find dimensions. And what are we doing? We're optimizing volume. As soon as I see that word largest, that tells me what function it is I'm optimizing. So we're trying to find the dimensions of the box, X, Y, and Z, that maximize, because we want the largest volume, the volume V. And I know that the volume of a box is just length times width times height, so that's X times Y times Z. Okay, so after stating everything that's given, we need to write this a little differently so that we can actually answer the question. Notice that we're asked to maximize, this function of 3 variables, and we're in Calculus 3, so we only know how to maximize functions of 2 variables using the second partials test. So that means we need to write this function that we're optimizing entirely in terms of 2 variables rather than 3. Now, whenever that happens, you know that there is some constraint equation out there. Or in other words, there's some equation that relates X, Y, and Z to each other. It constrains that relationship between the variables. And actually, I think it's going to be given by this. As soon as they told me that I had a fixed cost, or a, what did they say? For a fixed amount of money C, I knew that that was going to be my constraint. So there's going to be an equation associated with this total cost that tells me how X, Y, and Z must be related to each other. Once I know how X, Y, and Z must be related to each other, given that constraint, I can write this function in terms of 2 variables only, and then I can optimize it using the methods that we've discussed, which include the second partials test and everything associated with that. Okay, so I've got my game plan. I know I want to find the total cost. And then we will use that equation that relates x, y, and z to write this function v in terms of two variables only. Okay, well, in the problem statement, we're told that the material for the base costs a different amount than the material for the sides. So I know that if I want to find the total cost, I need the cost for the base, and I need to add that to the cost for the sides. Let's find the cost for the sides first. Now, I actually don't know how much the material for the sides costs. All I know is that the material for the base costs 1 times as much per unit area as the material for the sides. So I'm going to define a variable so that I can find the cost for the sides in terms of this variable. So I'm going to let rho equal the cost per unit area for the material for the sides of that box. Well, then the cost for the sides is going to be the cost per unit area times area for each of these sides. Then we're going to add them all together. So I'll just put a summation there to say this, that's the sum for each side, or that's the sum over all four sides there. Okay, so the cost per unit area is defined to be rho. And then I want to multiply by the area of each side. So that left side and right side, so that's that side over there, and then this side over here, those have the same dimension. Those are both x times z units of area, units squared. So we have rho times x times z for those, but then I have two of them, so I'll multiply that by 2. And then the front and the back have the same area. So this front side has an area of y times this dimension. Well, that's our z. Excuse me. And the back side has the same dimension. So this is 2 times rho times y times z. Rho times y times z is the cost for that front side, and then you've got the same cost for the back side because it has the same dimensions. Okay, so that's the cost for the sides. Now the cost for the base can be handled similarly. We want the cost per unit area for the base, and then we want to multiply that by the area of the base. But this time, we were told that the cost per unit area for the base is 1.5 times the cost per unit area for the sides. So the cost per unit area for the base is 1.5 times rho. And then the area of the base, well, the base has dimensions x and y, so that'll just be x times y. So the total cost is this cost plus this cost, and we're told that the total cost C is fixed. So we have C equals 2 times rho times x times z plus 2 times rho times y times z plus 1.5 times rho times x times y. And if you want to, you could divide everything by rho. So if C over rho equals 2 times x times z plus 2 times y times z plus 1.5 times x times y. So that is our constraint equation. This tells us how x, y, and z must be related to each other. If we have a constraint equation, it will allow us to write that function of 3 variables that we're trying to optimize in terms of 2 variables so that we can use the methods that we've studied in Calculus 3. So in order to do that, we need to solve for one of these variables in terms of the others. Since that's an xz and that's an xy, and that's a yz and that's an xy, and that's an xz and a yz, it's not really easier to solve for any one of the variables in terms of the other two. So I'll just choose to solve for z in terms of x and y. So if I'm solving for z in terms of x and y, I need to get rid of this term that does not have a z in it. I'll move that to the other side. So we have c over rho minus 1.5 xy is equal to this expression involving z. I will factor out the z. So I've got 2x plus 2y times z there. And then I'm getting z by itself, excuse me. So we will divide both sides by 2x plus 2y. So we found the total cost, that was our constraint. And then we find that z in terms of x and y. And remember, the reason we're doing that is because we want the volume in terms of two variables only. Next, we're just going to substitute this for z in the volume equation, and then the volume will be written in terms of two variables only. So we're here now. Volume is x times y times z, but z turned out to be c over rho minus 1.5 x times y, all divided by 2x plus 2y. I would write that xy as itself over 1 and then distribute. So we've got c over rho times xy minus 1.5 times x squared times y squared, all divided by 2x plus 2y. So now you've got z as a function, or v, excuse me, as a function of two variables, and we can optimize that using the second partials test. Okay, now remember, when you're using the second partials test, the first thing you need to do is find the critical points. Now in Calculus 1, when you found the critical points, you were setting the derivative equal to 0 and solving for x, and then thinking about where that derivative was undefined. Similarly, we want to, well, we're going to do something similar here, but instead of using the derivative, we use the gradient vector in Calculus 3. So we want the gradient to be 0 or the gradient to be undefined. So we'll compute the gradient of capital V, and then we'll find critical points. So that's finding xy such that the gradient is equal to the 0 vector, which means the partial of v with respect to x is equal to 0 and the partial of v with respect to y is equal to 0 at the same time, so that the gradient is equal to 0. And of course, we're looking for xy in the domain, and the domain is the x and y values that make sense for this problem. And remember, we're talking about a box. So if I'm talking about a box, x and y have to be positive numbers. Okay, so let's start by computing the gradient. Now notice we've got some symmetry here. If I replace x with y, this would still be, instead of xy, I'd have yx, but that's the same thing. If I replace x with y, I'd have the same thing there. And if I replace x with y down here, I'd have the same thing. So because of symmetry, the partial of v with respect to x and the partial of v with respect to y are going to be very similar. I can just use the partial of v with respect to x to find the partial of v with respect to y due to symmetry. That way we don't have to do this calculation twice. We're going to get the same, I want to say same formula for the answer. It's not exactly the same, but you'll see because of the symmetry. Okay, so first we want to take the partial of this function with respect to x. And since it's a quotient, it makes sense to use the quotient rule. So with the quotient rule, we say low bottom function, d high with respect to x, treating y as a constant. Well, the derivative of this constant, or I'm thinking of this as a constant times x, the derivative of this constant times x is the constant. And then over here, I'm subtracting the derivative of this with respect to x, treating y as a constant. The derivative of 1.5x squared with respect to x is 1.5 times 2, that's going to be a 3, times x to the first. And then the y squared is a constant, so we can bring that down. That's low d high, bottom function times the derivative of the top function minus high d low. And the derivative of the bottom function with respect to x, treating y as a constant, is just a 2. All over low low, bottom function squared. So let's distribute. So I have this c over rho times 2 times x times y. It's first times first, outer times outer is minus 6x squared y squared. Inner times inner is plus 2c over rho times y squared. And then here I'll distribute the negative 2. So I have negative 2 times c over rho times x times y. And a negative 2 times a negative 1.5 is going to be a positive 3 times x squared times y squared. And I'm looking for any cancellations. You see I've got one of these guys and one of these guys. That's good. Those are gone. What else? Oops, I think I missed a term. We did first times first here, outer times outer, and then inner times inner. I think I forgot to do last times last. That minus, we should have a minus a 6xy cubed there. I'm sorry about that. Yeah, that's the last times last. So those guys are gone. And then I've got a negative 6x squared y squared and a positive 3x squared y squared. So that can be combined into a negative 3x squared y squared. All over 2x plus 2y quantity squared. So we've got 2 times c over rho times y squared minus this 6xy cubed, that last times last term that I missed the first time. And then this plus this gives me a negative 3x squared y squared. All of that is divided by 2x plus 2y quantity squared. All right, now because I can switch x and y here and I get the same expression, the partial of v with respect to y is going to be very similar. Just everywhere I see an x, I should write a y, and everywhere I see a y, I should write an x. That's what we would get if we differentiated with respect to y instead of differentiating with respect to x. So we have 2 times c over rho times x squared this time, minus 6 x cubed times y. I would normally write y x cubed if I was switching x and y, but usually we like to write these expressions alphabetically. Switching x and y again doesn't change anything on that last term. And it doesn't change our denominator either. 2x plus 2y is the same as 2y plus 2x. So we get that. Now both of these have to be 0 at the same time. In order for our gradient to equal 0. Now each of these is a fraction. The only way a fraction is 0 is if the numerator is 0. So the partial of v with respect to x is 0 when 2 times c over rho times y squared minus 6x times y cubed minus 3x squared times y squared is equal to 0. And similarly, this bottom function is equal to 0 when the numerator is 0 as well. Okay, so we've got that equals 0 and that equals 0. Now, usually if I'm solving an optimization problem and I've got two polynomial equations, the easiest way to get started is to factor those polynomials as much as possible. So I've got a 2, a -6, and a 3, so I can't factor out a constant. But I do have a y squared, a y cubed, and a y squared there, so I can factor out a y squared from that first one. And then I'll be left with this. And because of the symmetry, I can factor out an x squared from this one. Now to solve this system of equations, I say, well, how can this first equation be 0? I guess these aren't equivalents. It's really just an implication. Okay. I say, how is this times this, how could this times this possibly be 0? Well, this could equal 0 if y equals 0, so that's one possibility. If y equals 0, then the second equation reduces to x squared times 2 times c over rho. And if y is 0, both of those terms are 0. Now we're assuming we have a fixed cost and we're assuming that cost is positive. In that case, if I have constant times x squared equals 0, that means x is equal to 0. So the critical point here is xy equals 0, 0. That's for this system of equations. But that's actually not in the domain of our function when we're thinking about the real world application of finding that maximum volume of a box. X and y can't be 0. If x and y were 0, then we wouldn't have a box. So we're going to have to do something else. So that is a critical point of, or that is not actually a critical point of this function. It would have been if the denominator wasn't 0. But this is a solution of this system of polynomial equations. It's just not a solution that we're looking for because it's not in the domain that is implied by the application that we're examining here. So, okay, this times this equals 0 if y equals 0, and that leads to something that doesn't make sense for our application. So the only other way that this first equation could be 0 is if this expression is 0. So we have 2 times c over rho minus 6xy minus 3x squared is equal to 0. And then we also want the second equation to be 0. Okay, now again, if this is 0 and this is 0, well, the only way this could be 0 is if this equals 0 or this equals 0. Now, if x equals 0 and I substitute up here, I get this cost must be 0. So that's not possible. So we want this and this to be 0. Since x equaling 0 leads to something that's not possible for our given application problem, this is actually going to imply that we've got these two equations that must be 0 at the same time. 2 times this constant minus 6xy minus 3x squared has to equal 0. And 2 times that constant minus 6xy minus 3y squared also must be 0. Let's take this and solve for x and y. Now I'd really like to get rid of this mixed term. One of the easiest ways to do that is to just multiply this first equation by -1 and then add these two equations together. Then the constants reduce, then these guys reduce, and we just end up with 3x squared minus 3y squared equals 0. And if that's true, We must have that, and that means that x squared must equal y squared. And that means that y must equal plus or minus x if you take the square root of both sides. Now, y equals negative x is not going to work because x and y have to be positive numbers because we're talking about this application. If you've got y equals x and y equals negative x as possibilities, and x and y both have to be positive, that's not an option. So we're going to choose that one. So now the question becomes, okay, if y is equal to x, what do y and x have to equal? So I will substitute y equals x in up here, and then we'll solve for x. Okay, so now we're here. I've got 2 times c over rho minus 6 times x times y, and y equals x, minus 3x squared equals 0. So 2 times c over rho minus 9x squared equals 0. And we can add this to both sides if we want to. I was thinking we could subtract that from both sides, but I'd just like to make everything positive. Then let's take the square root of both sides, and we'll take the positive square root. Because we know that x has to be positive. And then we can divide everything by 3. So x is equal to this value, and since y and x are the same, y must be the same thing. Now, I don't know why WebSign chose to do this, but I think that they just decided that rho was equal to 1. It doesn't make sense. This x and y value actually do depend on that cost per unit area of the material for the sides, but they didn't give that to you. So they said, let's just assume that the cost per unit area for the material for the sides is $1 per unit area. In that case, our x value is 2, or the square root of 2c over 1 divided by 3. So that's the square root of 2c over 3. Y is the same because x and y were the same from earlier. And then the z value was given by this function. It was c over rho minus 1.5 times x times y. And x was this value, and y was this value. And then we're dividing by 2 times x plus 2 times y. And then there's a little bit of arithmetic that we have to do to get z by itself. So we've got c over rho there. I would call that 3 over 2 just to make the arithmetic easier. That square root times that square root just gives me a 2c. And then I've got a 9 right there. Well, that 3 goes into that 9 3 times. The 2's reduce as well. So we've got that. And in the denominator, you've got 2 over 3 of those plus 2 over 3 of those. That's 4 over 3 of those. And I forgot rho is equal to 1. So this is c minus 1/3 of c. So it's going to be 2/3 of c in the numerator. And then we've got this 4/3 times the square root of 2c down here. And the 3's reduce. And now you've just got a c over 2 times the square root of 2c. And if you want, you can multiply by root 2c over root 2c, which gives you c times root 2c. And this is going to be 2c times 2, which is 4c. And those reduce. And I believe That is your z value. Okay, so we just found the z value that goes with this choice of x and y, but we never actually used the second partials test, did we? All we did was find the single critical point and then find the x, y, and z associated with it. Now we should always use the second partials test to make sure that the critical point that we found actually corresponds to a maximum and not a minimum. That's what we're talking about here. We want the maximum volume. We don't want to accidentally minimize the volume when we intended to maximize it. So let's make sure that we did that. Now remember, our partials of z with our partials of v with respect to x and y were given by these expressions. We had c over rho times, I'll try to find that paper. There it is. Or 2 times c over rho times y squared minus 6xy cubed minus 3x squared y squared, all divided by 2x plus 2y, and that's being squared. And now we've made the choice of rho equals 1 because I saw in WebAssign that they didn't include that dimension for that cost per unit area, or that factor of cost per unit area. So this is the partial of v with respect to x. Oops, there should be a c there. And that's just because I'm using rho equals 1. And the partial of v with respect to y is very similar. So I've got 2c times x squared minus 6 times x cubed times y minus 3x squared y squared, all divided by 2x plus 2y, quantity squared. Okay, so I've got that, and I need to be sure that this critical point that we found, xy equals square root of 2c over 3 and square root of 2c over 3. I need to be sure that that corresponds to a maximum and not a minimum. So, or not a saddle point as well. I mean, we want to make sure that we're actually maximizing the function when we intend to maximize the function. So we need to take second partials of these guys. I know, it's a lot. But just to be sure, if I use the quotient rule here, we have the bottom function times the derivative of the top function with respect to x, treating y as a constant. The derivative of this piece is 0. And if x is my variable, this is a constant times x. The derivative of a constant times x is just the constant. And over here, I've got a constant times x squared. The derivative of a constant times x squared is just that constant times 2x. So I'm going to have 6x here times y squared. That's low d high minus high d low. With respect to x, I have to use the chain rule. We'll have 2 times that inside function times the derivative of the inside with respect to x, which just gives me an extra 2. All over the bottom function squared. All right. And if we factor out that 2x plus 2y that we've got here and here, this is what we're left with. Over here, I still have another 2x plus 2y and this expression. So we should distribute. And then since I factored out this, I'm just left with a 4 times a negative 1 times this. So I'll distribute a negative 4 to all of that. And all of that is being divided by 2x plus 2y raised to the 4th. All right, now if I distribute here, first times first is going to give me a 12xy cubed. Outer times outer is negative 12x squared y squared. Inner times inner is negative 12y to the fourth. And last times last is negative 12xy cubed. I'm just bringing everything else down. And eventually I'm going to look for like terms. Okay. And let's see, do I have any like terms? This negative 12, well, let's see, 12, 8, 24, and 12 all have a factor of at least 4 in common, so we can factor out a 4. Is there anything else we can factor out? I don't see anything else. But I do see a negative 12x squared y squared and a positive 12x squared y squared, so those guys are gone. And then I've got an xy cubed here and an xy cubed here and an xy cubed there. That's nice. Negative 12 plus 24 of those is 0. Very nice. So I'm just left with this negative 12y to the fourth. If I factor out the 4, I have a negative 3y to the fourth there. And then a minus 2c times y squared. I guess we could have factored out a y squared as well. So you've got 4y squared times a negative 3y squared minus 2c. I guess we could have factored out a negative as well. I'm sure this happens to you guys too. You start to factor and then you say, hey, I forgot this other thing I could have factored out. We could simplify that denominator with a 4, but it's not necessary. So I think I'm just going to leave it alone. Okay, so that's the partial of v with respect to x twice, or the second partial of v with respect to x. Now, I talked about symmetry before. Since that function v of x and y was symmetric with respect to x and y, meaning that I could switch x and y and I got exactly the same function. The second partial of v with respect to y is going to look just like this, except everywhere I see a y, I'll replace it with an x. So we'll have negative 4x squared times 3x squared plus 2c all over 2x plus 2y quantity cubed is going to be 2y plus 2x quantity cubed, but that's the same thing. All right, so I've got that and I've got that. Now I need to find the second partial of v with respect to x and then y. So I'm going to take the partial with respect to y of the partial of v with respect to x, which was 2c y squared minus 6xy cubed minus 3x squared y squared all over the quantity 2x plus 2y squared. So we have here the bottom function times the derivative of the top function with respect to x, treating y, or with respect to y, treating x as a constant. The derivative of this piece with respect to y is 4cy. Derivative of y cubed with respect to y is 3y squared. So we're going to have 3 times that negative 6 is negative 18 times x times y squared. And then I've got a constant times y squared here. The derivative of a constant times y squared is that constant times 2 times y. So that's low d high minus high d low. So we have 2 times 2x plus 2y. It's derivative of the outside evaluated at the inside times the derivative of the inside with respect to y, which is just another 2. That was by the chain rule. All of this is divided by 2x plus 2y squared and then squared again, so raised to the 4th. So now I've got a 2x plus 2y over here and I've got another one over here, so I want to factor that out. And then I'm left with 2x plus 2y times this quantity. I think I'll distribute the 2x first. So I'll have 8cxy minus 36x squared y squared minus 6, oops, I'm distributing a 2x, minus 12x cubed y. And then I will distribute the 2y next. So I'll have plus 8cy squared minus 36xy cubed minus, this times 2y is negative 12x squared y squared. That's a lot. That's just this part. Okay, I'm just going to end there because I'm running out of space. So I've got that as my first expression in the numerator. And then all of that is actually going to be added to this. Now I would typically just have the 2x plus 2y here because I had factored it out from both this term and this term. It's not really a term, but it's separated by subtraction. So we're sort of thinking of it as a single group. I've already factored out this 2x plus 2y from both of these guys. The remaining 2x plus 2y times this was giving me this here. There's 1, 2, 3, 4, 5, 6 terms because I had a binomial times a trinomial. Now over here, after factoring out the 2x plus 2y, I just have a negative 4 times that. So I will multiply that negative 4 times this expression now. So we'll have negative 8cy squared plus 24xy cubed plus 12x squared y squared. And all of this is divided by 2x plus 2y to the 4th. This 2x plus 2y will reduce with one of these guys down there. And so we'll just have this plus this in the numerator over 2x plus 2y quantity cubed. Okay, now just keep going. See if there's anything that reduces. I've got a negative 8cy squared and a positive 8cy squared, so those guys are gone. I've got a negative 12x squared y squared and a positive 12x squared y squared, so those guys are gone. And then I have a, I don't think anything else reduces. These are like terms though. So I've got an 8cxy minus 36x squared times y squared. And then this is x cubed y, so it's different. So it's 12x cubed times y. And this negative 36xy cubed plus 24xy cubed is going to give me a negative 12xy cubed. All over 2x plus 2y quantity cubed. And we could factor out an x and a y. And a 4. So you have 2c minus 9 times x times y minus 3 times x squared minus 3 times y squared, all divided by 2x plus 2y quantity cubed. Man, that's a lot. But now we've got this one. This is the partial of v with respect to x and then y. We could also find the partial of v with respect to y and then x, but it's going to be the same thing. So we'll just say that those are the same. All right, now we wanted to use the second partials test, which requires evaluating all of these partial derivatives at a particular point, at our critical value. And remember, this was our critical value. So I've got x and y are both square root of 2c over 3. So if I'm evaluating this second partial of v with respect to x at square root of 2c divided by 3, I I have negative 4 times y squared. That's square root of 2c divided by 3 squared. Times 3 times y squared again, square root of 2c over 3 squared, plus 2c. All of that is divided by 2 times x, square root of 2c over 3, plus 2 times y, square root of 2c over 3, and that's all being cubed. And so what we get is negative 4 times 2c divided by 9 times this quantity, 3 times 2c divided by 9 plus 2c. And this goes into that 3 times. And then in the denominator, I've got 2/3 of these and then 2/3 more, so that's going to be 4/3 times the square root of 2c, and all of that's being cubed. So I've got 2c over 3, and then this is 6c over 3. So that would be 8c over 3 there. We've got negative 8c over 9 times 8c over 3 divided by something positive. We're going to have 64 over 27 times 2c times the square root of 2c down there. 27's reduce. 8 times 8 is actually 64. So we end up with negative c squared over 2c times the square root of 2c. One of those will reduce. In any case, it's negative. That's what we need. We could simplify this further, but I think I'll leave it alone. By symmetry, this is also negative. And let's find those mixed partials. And this is, of course, at the critical point. All of these are evaluated at the critical point. I didn't write that in my notation, but I should have. This is 4 times x times y times 2c minus 9 times x times y minus 3 times x squared minus 3 times y, squared. All of that is divided by this denominator again, which I already know to be 4 over 3 times the square root of 2c, quantity cubed. So after some simplification, we will have negative 8c over 9 out front here. And then we've got 2c minus, and this is going to be 9 times 2c, or actually that the 9's will reduce. It's going to end up being a 2c. And then we'll have minus this, which will be 2c over 3, minus another 2c over 3. Those reduce. And then down here, we're going to have this cubed, so 64 over 27. And then we'll have 2c times the square root of 2c. If we simplify further, this is going to be negative 4c times negative 8c is 32c squared over 27. And we can multiply by the reciprocal of this. So we'll have 27 over 64 times 2c times the square root of 2c. The 27's reduce. 32 goes into 64 twice. So we end up with c squared over 4 times c times the square root of 2c. One of those c's will reduce. So we have c over 4 times the square root of 2c. Oh, all of that to get to the point where we could take the determinant of this matrix at our critical point. And these guys both had the same value. We had negative c over 2 times the square root of 2c. These were the same, so that'll be squared. And then these guys had the same value. It was that value right there. You want to square the numerator, square and square the denominator. They don't have a common denominator, so I'll multiply this guy by 4 over 4. We end up with 3c squared over, looks like 32c. So those reduce. So D is positive. That is our determinant. Since D is positive, and that second partial of B with respect to X was this number here, which we know to be negative, then it's concave down in the X direction, concave down in the Y direction, and that means that that XY pair that we started with was our critical point. Gosh, that was a lot. But it was important that we did it because we want to be sure that we're actually maximizing that volume and not minimizing that volume. So it turns out that the volume is maximized at this XY pair, and it's been a little while since I found the Z value that went with that, but X is equal to square root of 2C over 3, and Y is equal to square root of 2C over 3. Now I'm going to try to find the Z value in all the work that we just did. I tend to stick these in the recycling pile pretty quickly. I don't remember where that went, but that's okay. X will have this value and Y will have this value, and to find the corresponding Z value, you can just replace X and Y down here into this formula where rho is equal to 1. So you have C times 1.5 times X times Y, all divided by 2X plus 2Y. Oops, I keep making that square root too large. And so we end up with 4 of these in the denominator. And up here, this is a 3 over 2. You can think of it that way. So one of those 3's will reduce. And what we end up with in the numerator is C minus 2C divided by 2 times 3. So those will reduce. And so we'll end up with 3 over 3 times C minus 1 over 3 times C. So 1C minus 1/3 of C is 2/3 of C. And we get that, and those reduce, and you end up with a C over 2 times the square root of 2 times C, or if you want to rationalize, you may. So we'll have 2, or C times root 2C over 2 times 2C, and the C's reduce, and you get root 2C over 4 as the Z value. Got a little messy there at the end. And that is it. That is how you solve that problem. Finding the critical point was a little tricky. And then it's really important, I want to emphasize it, it's very important that you actually determine that that's maximizing your function and not minimizing it, because you don't want to accidentally find the minimum value when you're looking for the maximum value.